What happens when many agents share one environment and must act at the same time? Some collaborate, some compete, and some do both. Understanding those interactions helps you see how multi-agent systems produce larger system behaviors. A multi-agent environment contains multiple agents that interact within a shared setting. Those interactions may involve collaboration, competition, or both. They are central to designing effective multi-agent systems because local actions can produce wider system outcomes. Agent interactions can be collaborative, competitive, or mixed mode. Collaborative interactions support shared goals. Competitive interactions involve conflicting objectives. Mixed mode environments combine both, such as vehicles that cooperate to avoid congestion while still seeking better routes. Communication lets agents share information, negotiate, and coordinate actions. In direct communication, agents exchange explicit messages, and standards such as the Foundation for Intelligent Physical Agents help structure that exchange. In indirect communication, agents respond to shared environmental changes, as in stigmergy. Decentralized coordination relies on local interactions, which makes it scalable and robust, as shown by autonomous drones adjusting flight paths to avoid collisions. Negotiation helps agents resolve conflicts and allocate resources efficiently. It can use auctions, bargaining, or contract net protocols. Cooperation helps agents work together through task decomposition and role assignment, such as multi-robot systems dividing work to improve efficiency, 0-5. As agent numbers rise, communication grows harder, conflicts increase, and different capabilities or protocols make smooth interaction more difficult. Interaction protocols standardize how agents communicate and collaborate. The contract net protocol supports decentralized task allocation. Auction mechanisms support bidding for resources or tasks. Game theoretic models analyze strategic interaction, and the Foundation for Intelligent Physical Agents standard supports consistent communication across agents. Agent interactions appear in healthcare, transportation, finance, supply chains, and environmental science. Hospital systems use direct communication for real-time updates. Autonomous vehicles use decentralized coordination. Trading bots use strategic models, supply chains use contract net allocation, and ecological simulations use indirect communication. Multi-agent interactions offer scalability, adaptability, emergence, and fault tolerance. At the same time, they bring complexity, unpredictability, resource overhead, and ethical concerns. These strengths and limits explain why interaction design matters as much as agent autonomy. Cooperation in agent systems is about agents working together to achieve shared goals or solve complex problems. Two main frameworks are teamwork and joint intentions and collaborative problem solving. Both aim to support efficient communication, coordination, and distributed problem solving. Their main characteristics are shared goals, role assignment, commitment, and mutual awareness. Teamwork and joint intentions align goals, beliefs, and actions across agents. In the joint intentions framework, agents commit to a shared intention, maintain beliefs about progress, and communicate to stay aligned. Collaborative problem solving is used when a problem is too complex for one agent alone. Agents break work into subtasks, coordinate actions, share intermediate results, and resolve conflicts. Techniques include distributed constraint satisfaction problems, distributed search, and negotiation-based approaches. In collaborative problem solving, protocols guide how tasks and strategies are shared. The contract net protocol lets a master agent broadcast tasks and worker agents bid. Game theoretic models can support cooperation for collective utility. Compared with teamwork, this model focuses more on distributed roles and negotiation. Competitive behavior appears when agents face conflicting goals or limited resources. Game theory provides a framework for analyzing these situations. It helps explain strategic behavior, equilibrium states, and the mechanisms that shape outcomes in adversarial environments. Resources remain limited. Important concepts include Nash equilibrium, dominant strategies, and payoff matrices. Nash equilibrium describes a stable state where no agent improves payoff by changing strategy alone. A dominant strategy gives a better payoff regardless of others. And payoff matrices show outcomes for strategy combinations. Mechanism design creates rules that encourage desired behavior among competitive agents. It includes incentive alignment and market mechanisms for efficient allocation. Game theoretic tools appear in finance, supply chains, electronic commerce, energy markets, and traffic management. Different approaches serve different aims. Nash equilibrium focuses on stability, mechanism design focuses on crafting rules, and competitive negotiation focuses on maximizing individual payoffs through interaction. Computational markets and auctions structure resource allocation, coordination, and decision-making among agents. Market-based coordination uses supply, demand, and pricing dynamics. Its key features are decentralization, efficiency, and dynamic adaptation, though limits include market failure, agent modeling demands, and computational intensity. Auction models include the English auction, Dutch auction, and Vickrey auction. Agents may use incremental bidding, aggressive bidding, or truthful bidding depending on the rules. Challenges include information asymmetry, dynamic market conditions, and collusion risks, even though auctions support scalability and fair resource allocation. Automated negotiation models help agents reach agreements in resource allocation, conflict resolution, and collaborative decision-making. Bilateral negotiation uses two-party interaction, iterative proposals, and utility maximization. Multi-agent bargaining adds coalition formation, voting, auction-based bargaining, and consensus-based negotiation. 02, 03, 04, 05. When goals cannot all be satisfied, conflict resolution becomes essential. Methods include mediation, arbitration, compromise solutions, and game-theoretic approaches based on Nash equilibrium or Pareto optimality. These methods support fairness and long-term cooperation, but they may require oversight and significant computation. You have seen how agents communicate, coordinate, negotiate, cooperate, and compete inside shared environments. You have also seen the main cooperation models: competitive game theoretic tools, computational markets and auctions, and automated negotiation models. Together, these interaction methods shape effective multi-agent systems across many domains.